At this stage, since we already know the whole structures of the FGK decision forest, it's time for us to make the predictions of the protein 3D structure. The only question is this: unlike classification, we predict a label. Basically, we go to walk or we not go to walk. That's a very easy yes or no classification. Now the question is, if when we try to predict a protein 3D structure, what are we really predicting? It's not going to be simply as a yes or no answer, because the 3D structure is in 3D space. And therefore, we need to look into how do we store the 3D information of the protein. To look into that, you need to understand, and we already see that in PDB, 3D structure are listed as XYZ, three-dimensional space coordinations. So how do we present the 3D structure in our data set? In other words, we see this picture in our chapter 2 presentation before. For one protein, it has 180 primary sequence information. It has 9 positions of the secondary structure. Now, how do we store the three-dimensional information over here? Let's take a look of an example. Say now we only have 4 elements. Window size equals to 4 instead of 9 that we are using. And we try to simplify it as in a 2-dimensional space. But of course, it can extend the same concept into 3-dimensional space. Say now we have 4 points and we want to store their relative distances with each other. Once we have that, all mutual distances, we can reconstruct the structure of the proteins that we are looking at. And therefore, say now we have 4 elements here, what we need to do is that we need to look into the distance between point 1 and 2, point 1 and 3, point 1 and 4. And we need to store those 3 distances. Then we go into the other 2 distances from point 2 to 3, 2 to 4, and of course, finally 3 to 4, so that we will be able to store all of the distances to each other, and by using that, we will be able to reconstruct the original 3D space of the element. And that's why if we have 4 elements, we need to store 3 plus 2 plus 1 distances. In other words, in our experiment, the window size equals to 9. That means we need to store 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 distances equal to 36 distances. And of course, because they are in 3-dimensional space, the distance calculation formula that we choose is going to be Euclidean distance. And that's why in our data set, this is how we store the 3-dimensional information. 180 dimension of the primary sequence, 9 position of the secondary structure, and 36 3-dimensional structure information. And that is how we store one full data set that incorporate primary, secondary, and tertiary structure of a protein. To make sure you guys understand it, I want you guys to have a simple assignment. So in this assignment, I'm going to take a look of the protein database data that I've showed you before. I want you to calculate the first 9 C-alpha carbon mutual distances in one AVW PDB file with Euclidean distance. So basically, you need to calculate those 36 distances based on the C-alpha carbons of the protein from first location to the 9th location. It's kind of interesting thing for you to see, so I really want you to open up the PDB file, take a look of that, and try to understand where are the C-alpha carbon located. And of course, to make sure you guys doing it correctly, I have listed out first 9 positions C-alpha carbon. So you can see that the first atom is the C-alpha carbon, the first protein is ILE, and it has its three-dimensional space over here. The next item, the next protein is amino acid is VAL, and the C alpha carbon is located at this X and Y and Z location. So for your convenience and for you to verify your search, I have listed all of those 9 C alpha carbon locations here. So all you need to do is calculate the mutual distances to store the structure of this protein segments that I have listed over here. So this is an assignment. I want you guys to submit that through the Blackboard so that you can have some practice understanding how do we store the 3D structures. So by knowing that, to evaluate our prediction, basically our prediction will try to find 36 spaces of the C alpha carbon mutual distance. And we want to make a prediction, and we can evaluate, look into the real proteins mutual distances of that data segment. So we can compare our predicted one versus the original one. So we want to find the distance between each other, and then basically take the Euclidean distance check on each locations that we predicted, and we average by 36 locations that we have, and we can see that averagely for every locations that we evaluate, what is the difference between our predicted one as well as the real one. So we use this RMSD to evaluate the prediction, rho mean square deviation. And therefore, through this approach, we first compare with the results by using only the FGK model. So FGK model generates a lot of protein sequences, protein sequence motifs. And I want you guys to be able to read this table. This is a pretty complicated table, so let's take a look at this. The FGK model, what we try to do, on this part of the table, we only pick out the protein sequence motif with greater than 80% secondary structural similarities. So they are very small, selective motifs, few of them, but they are very conservative. They have very strong structures. And so what we're going to do is that for all the testing data set, we try to find the distance between the testing data set with these protein sequence motifs that are greater than 80% secondary structural similarities. As long as the distance is less than 550, we try to make the prediction. So that we need to find the closest one. And if they are closer than distance of 550, then we make the prediction. If they are higher than 550, then we don't make the prediction. That's what this distance is trying to do. Of course, the shorter the distance, the coverage, the number of segments that we can make the prediction is fewer. And you can see that when we set a very strict rules over there, then what we can see is that we can only predict 0.061% of the testing data set, so very small of them. When that's happening, we want to see 55% of those predictions are less than 0.5 angstrom, which is the evaluation we talk about, the RMSD. The lower, the better. So if we say now how many of those segments that we predict is less than 0.5 angstrom, which means that they are very, very close to the real structure, and we only get 55% of that. If we lose that restriction to 1 angstrom, then 92% of those predictions are very good, and 95% of those predictions is actually less than 1.5 angstrom. So that is how we will be able to read the whole data. So you can see that when we goes up from distance of 550 to 1,300, now we can make 3% of the prediction. And remember, the whole purpose is in this research is that we want to predict protein local tertiary structure. So we predict a small segments with high confidence, and that's the whole purpose of what we are doing. And therefore, even though it's low percentage of the coverage, it is the purpose of the whole research. And you can see that when we comes to 1,300 distance threshold, we can see that 44% of those predictions, and you can see we have much more predictions than this one. The accuracy, the percentage of the predictions less than 0.5 Armstrong is lowering from 55 to 44. And for 1 Armstrong is 80%, 1.5 Armstrong is 87%. So you can see that those are some changes. When we predict more, the accuracy goes down a little bit, but you can see that if we set up as 1 Armstrong, we can still have 80% of the predictions that's less than 1 Armstrong of the RMSD evaluation. On the other side, if we use more motifs, now we look into the motifs that are greater than 70%, we can increase the coverage. So you can see that the coverage is actually increasing. So while we increase the coverage, the accuracy may go down. So in the greater than 70% motifs, 1 Armstrong wise, starting from 88% goes to 66%. So you can see that it's actually a big drop compared with the 80% motifs. However, the coverage goes up to 14%. So there's always a trade-off between the two things, and that is how we will be able to use the motifs to predict protein local tertiary structure. The next slide shows the FGK decision forest. So this one is adding the decision forest, which is the main thing that we want to discuss here. So while we have the decision forest, is that not only we look into the similarities, closest sequence and the distance is less than 550, we also need to feed in the decision tree to see if this testing segment really belongs to these motifs. And therefore, with that additional setup, the coverage is even lower compared with the previous FGK result. However, you can see the accuracy can goes up, so that it goes up to 74%, which is a very big achievement that of the predictions are less than 0.5 Armstrong. And the accuracy, this is goes to 90 to 95, and this is with the distance of 1300, it's going to 82% to 88%. So we add one more layer of the checking, so we will lower the coverage but increase the prediction accuracy. The next table is the comparison of that. So you can see that by using the FGK model, FGK decision forest model, the coverage drops a little bit. It's not a lot, so you can see that for a distance of 550, it's only like 0.002% reduced, but the accuracy wise increase quite a lot. For 0.5 Armstrong, predictions is actually increased about almost 20% of the accuracy. There's some exceptions that we mark in red for the prediction accuracies, but you can see majority of them are increased dramatically. Basically, you can see that this one with the highest distance using 80% of the motifs, the accuracy in 0.5 Armstrong criteria, we increase 17%. So that this is actually adding one more layer, and then make sure that we would be able to have even stronger predictions in their protein 3D structure. So the conclusion is that by adding this decision forest layer, we can successfully have a much better prediction for the protein local 3D structure with a little bit loose of the coverage, but it's still acceptable based on the table that we have just seen.